All right, our lesson today is going to be about implicit differentiation. So we're going to learn how to take the derivative of functions that are defined implicitly rather than explicitly. Okay, so explicitly defined functions are these ones on the left. These are things that we already know how to take the derivative of. They're explicitly defined because the y variable or the output variable is by itself on one side of the equal sign, and all of the input variables are on the other side. Okay, implicitly defined functions have the input and output variables mixed together. All right, so we are going to learn how to take the derivative of functions that look like the ones on the right today. All right, so here is an implicitly defined function, and what we're going to practice here is differentiating with respect to different variables. So we're going to do letter A, we're going to differentiate with respect to t. Okay, in every problem, you must apply the chain rule. Okay, so every derivative will have a d something over dt as part of the derivative. Okay, so you're really applying the chain rule on every single problem that you do every single time. Okay, and it's just that sometimes the chain rule part is a times one, and we just don't write it. And so you probably haven't been thinking about the chain rule on a lot of problems because of that fact. Okay, I will really hammer that home here on this third example on letter C right here. All right, but for now, let's just practice how this works. So anytime you're doing an implicit derivative, it's always going to work this way. Okay, so we're taking the derivative of a y variable. I'll come down here, a y variable with respect to t. So you do the derivative like normal. You know how to do this. Apply the power rule, 3y squared. But you have to multiply by something. This is the chain rule part. Since y was the variable, we multiplied by the exponent, subtracted one from the exponent, but we kept the inside the same. So we have to multiply by the derivative of the inside. The derivative of y with respect to t is dy over dt. Okay, so you just put that every single time when you are doing an implicit derivative. So our next term is y squared, so we know how to take the derivative, 2y, but then I have to multiply by the derivative of y with respect to t, dy over dt. The next term is an x term. So I know how to take the derivative, minus 2x, but now I have to multiply by the derivative of x, which is dx over dt. So whatever variable you're dealing with, that goes on top, and then whatever variable you are taking the derivative with respect to goes on bottom. Okay, and then the last one is a constant. Derivative of a constant is 0. And again, technically we are multiplying by d something over dt, but since we're multiplying by 0, it's just going to be 0. So we just put equals 0 there. All right, this is it. This is the implicit derivative of that equation with respect to t. Okay, so I'd encourage you to try letter B on your own, which is basically the exact same problem, except you are doing it with respect to w instead of respect to t. Okay, give the video a pause, try it out, unpause, see how you did. All right, so you should have gotten, again, basically the exact same answer, 3y squared, and then we're multiplying by dy over dw, since we are taking the derivative with respect to w on this problem. Okay, plus 2y dy over dw minus 2x dx over dw is equal to 0. Okay, so I was mentioning letter C earlier, so here we go. Now we are taking the derivative with respect to x. That is the most common. Okay, we do a lot of problems where we take the derivative with respect to t, which we will get to in our next section. Okay, but if we're not doing it with respect to t, it's almost always with respect to x. Okay, so here's how this works. Same way, basically. We take the derivative, 3y squared, and then we multiply by dy over dx. Okay, just like the other problem. Second term, plus 2y, and we multiply by dy over dx. All right, third term, this is where it changes a little bit. So we still take the derivative, minus 2x. But then if we applied that same rule we've been doing, we would get dx over dx. Okay, and that is what I'm talking about. When we've taken the derivative, we've done a derivative of x squared before, right? Okay, we took the derivative of x squared with respect to x, and all we wrote when we learned how to do this was the derivative is 2x, and that's true and correct. Okay, so why does it look different here? Well, we're technically applying the chain rule, but what is this thing equal to? What is dx divided by dx? Okay, this might not be great math, what I'm about to say, but I mean, we're taking something and dividing it by itself, so that means that's equal to 1. So it's negative 2x multiplied by 1, and we don't need to write it if it's multiplied by 1. So that's what we've been doing the chain rule. We just haven't been writing that because it's not necessary, because it's equal to 1. All right, so I am just going to erase that now. You have it in the video to refer back to if you like. So the moral of the story here for this example is when you take the derivative of a variable and it's the same variable you're doing the derivative with respect to, then you do not have to include the chain rule piece because that's always going to be equal to 1. So the two y variables, we had to include dy over dx both times, but the x variable, we do not need to include that. All right, and then the derivative of a constant is equal to 0. All right, so what we're going to be spending most of our day on is doing problems just like this. And then we want to know the derivative, right? Hey, when we did our explicit problems like this one, I would have asked you, what is f prime of x equal to? And you would have been able to do it. You work it all out and you get f prime. I want the same thing for these. I want to know the derivative. Okay, now we're not calling it a prime notation. We're using this other notation. Okay, but I want to know, what is the derivative? What is dy over dx? So we do some algebra on this. I need to get my dy over dx by itself. Okay, so I'm going to take the term that does not have a dy over dx. I'm going to move that to the other side. 3y squared dy over dx plus 2y dy over dx is equal to 2x. All right, then we're going to factor the dy over dx out because they both have a dy over dx. That's going to leave me with 3y squared plus 2y. And then we saw over equals 2x over here. Okay, and then I'm trying to get the dy over dx by itself, so now it's multiplied by this thing. So let's divide by that thing, and that will do it. We're done. 2x divided by 3y squared plus 2y. So this is equivalent of saying f prime is equal to, or maybe I should use the y terminology. This is the equivalent of saying y prime is equal to this thing over here. You'll notice that our derivative is also defined implicitly now versus our derivatives being explicitly defined derivatives earlier. Okay, that's okay. Okay, we still have a derivative of an equation, and we can now use that derivative to do anything we want. Find the slope of a tangent line. We can set it equal to 0 to find where horizontal tangents are located. Anything we've done with derivatives already, we can do that with this implicitly defined derivative as well. All right, so I encourage y'all to try these on your own, especially letter A here, and you can unpause the video and see how you did. All right, so there is a little bit of a challenge here, so maybe you caught it if you did try it on your own, or maybe not. Let's see how we did here. So x squared, derivative is 2x. Since I'm doing the derivative with respect to x, I do not need to include a chain rule part. All right, the tricky part is here in the middle. This is a product of x and y, so you must use the product rule to take the derivative. Okay, so we do u times v. We do the derivative of u. The derivative of x is 1 multiplied by v, so multiplied by y. Since we took the derivative of x, I do not need to include a chain rule piece. Just like when I took the derivative of x squared on the first term, I did not include it. Second part of the product rule, plus keep the u, x, multiplied by the derivative of v. So the derivative of y is 1, but since I took the derivative of y, I need to also make sure I multiply by dy over dx. All right, so that middle term right there turned into this when I took the derivative. All right, so my last piece will be the derivative of negative y squared, which is negative 2y. That's a y, so make sure to include your chain rule piece, dy over dx, and then that's equal to 0 over there. Okay, it said find the derivative, so that means get dy over dx by itself. So I'm going to take these two terms that do not have a dy over dx. We're going to move those to the other side. Okay, I'm going to get rid of these times 1s as well. I don't need those. So x dy over dx minus 2y dy over dx is equal to negative 2x minus y. All right, now we are factoring out the dy over dx, leaving us with x minus 2y on the inside. And finally, we are dividing to get our dy over dx by itself. That's it. Okay, so be on the lookout for those product rules. Okay, another thing that I want to talk about before I move on to the next one. So when I said I'm taking the derivative of y earlier, I wrote it like this because I wanted to be very clear of what I was talking about. The derivative of y is 1, and then we do the chain rule where we multiply by dy over dx. From now on, when I take the derivative with respect to x of just a y, I'm going to say the derivative of y with respect to x is dy over dx. That's just what it is. I'm not going to write the 1 in front because it's not necessary. Writing a times 1 doesn't do anything for us. Okay, so just in the future, the derivative of y with respect to x is dy over dx. That's just what that derivative is going to be. Okay, let's move on to the second one. All right, this one is definitely a little more challenging. Hopefully, if you recognized the product rule on letter A, then I'm sure you recognize the product rule on letter B as well. So that's what we're doing here. U is cosine x, V is sine of y. So we're going to take the derivative of u, which is negative sine x, multiplied by sine y. Okay, since I took the derivative of the x part, I do not need to include my chain rule piece. Plus, keep the u, keep cosine x. Now I'm going to take the derivative of sine y, which is cosine y. Since I took the derivative of the y piece, I do need to include my dy over dx right there. Equals, this is a constant, derivative of a constant is 0. All right, trying to get dy over dx by itself. So I'm going to move this term. Okay, remember they're attached to each other with the multiply sign. So I'm going to add those over there. So cosine x, cosine y, dy over dx is equal to positive sine x sine y. And then I divide, and I have my answer. Dy over dx is equal to sine x sine y divided by cosine x cosine y. Hey, that answer is fully acceptable. You could recognize you have a sine x over cosine x, which is a tan x, and you have a sine y over cosine y, which is a tan y. So you could simplify it, and that looks a little nicer in its simplified form right there. All right. Mrs. Stephenson, who creates these notes, her students had TI-89s, so she has a bunch of stuff about the TI-89 down there. We have TI Inspires, but our TI Inspire CXs that we use in class do not do implicit derivatives. You must have a TI Inspire CAS version. So I will show you that if you do have a CAS version, or if you plan on getting a CAS version. I'll show you that here in a second. Okay, TI-83s, TI-84s, TI Inspire CXs do not do this. Therefore, implicit differentiation is always on the non-calculator part of the AP test. Okay, so they have to keep it fair for all calculators. So this is definitely going to be a non-calculator section problem. Okay, so here's how you would do it. You would go to menu. There's a calculus menu. Again, this is only on the CAS version. And then you've got a bunch of options there. And we should have, there we go, implicit differentiation all the way down, almost at the bottom. All right, so I'm going to click that. So imp diff, you could also just type that command from the keypad down here. It would have worked. All right, so let's see. I want to type in my equation. All right, yeah, we'll do this first one. So you type in the equation, and then you have to put comma x, comma y to tell it what the two variables are. Okay, so x squared plus xy minus y squared is equal to 3. So x squared plus x times y. You have to put your own times symbol, because if you don't, the calculator will treat xy as a variable, as a single variable, xy. Okay, so I want it to treat it as two separate variables, so I have to put my multiply symbol in there. All right, minus y squared is equal to 3. Make sure I got it right. Yes. All right, then I put comma x, comma y, just telling it what my two variables are. And there we go. So the calculator factored out a negative from my numerator, but otherwise, same exact answer that we got here. All right, so again, that's for the CAS version only. And since not everybody will have access to that on the AP exam, you would not see that question on the calculator part of the test. All right, last thing, find the second derivative. Okay, so this is how a second derivative is written in the Leibniz notation. That's what this notation is. It's Leibniz, Isaac Newton, and Mr. Leibniz. I should know Leibniz's first name, but I'm forgetting it at the moment. They both created calculus at the same time in two different countries, and so they both came up with the same ideas, but they had different notations. So we use a little bit of both. Newton's notation is the prime notation that we've seen. Leibniz's notation is this dy over dx notation. So this is how it works for a second derivative. And you can go third derivative, fourth derivative by just changing that exponent on the top and bottom. All right, so to be able to find a second derivative, we do the first derivative. Okay, so we're going to take the first derivative, 2y dy over dx. Plus, and there's our product rule again. So we just did this right up there. So it's the same thing. So it's 1 times y, which is y, plus x times dy over dx. This one's a worthwhile one to just memorize. You see a lot of x, y's in this section. So it's y plus x dy over dx. All right, then equal to 0. Derivative of constant is 0. Okay, so I'm going to do a couple steps at the same time because we do have to do a second derivative, so I'm going to kind of condense my work a bit here. So I know I'm going to need to factor out my dy over dx, and that'll leave me with a 2y and a plus x. Then I also know I need to move the term that did not have a dy over dx to the other side, so that's going to be a negative y. So now I can divide, and I have my first derivative. Negative y over 2y plus x. Okay, so now for the second derivative, we need to do a quotient rule on this. Okay, so second derivative is equal to low d high. So low is 2y plus x. D high, negative 1 times dy over dx. Again, I did not need to write my 1 there because I knew that it was, but I'm just trying to be as clear as possible on this first example. All right, minus high d low. So negative y, then times 2 dy over dx plus 1. My y got a little scrunched there. I'm going to rewrite that. Dy over dx and then plus 1. All right, then that's all divided by 2y plus x. All right, now what was not stated up here in the problem, but would most likely be stated on the AP exam, is find the second derivative in terms of x and y. And so technically what I have here is the second derivative. And if this isn't stated, this I would think would be an acceptable answer. However, this is almost every time I've seen a problem like this, it's always been stated in terms of x and y. So what that means is that this dy over dx right here and this dy over dx right here, those are unacceptable to have in my final answer because those aren't in terms of just an x and a y. Those are a derivative in there. Okay, so what we have to do to fix this is we have to take our dy over dx in terms of x and y, so this thing right here, and we have to plug that in for dy over dx over here. All right, so that's what I'm going to do now. So second derivative. Oh, I put my exponent in the wrong place up here. Second derivative, all right, is equal to, so I have 2y plus x, that's not going to change. I have this negative 1, I'm just going to put the negative in front like that. And then here's where I'm plugging in dy over dx. Okay, so I'm plugging in negative y over 2y plus x right there. Then I have a negative times a negative, so I'm going to write that as a plus y, parentheses. Then I have a 2, and then I'm plugging in my dy over dx once again, right here. Negative y over 2y plus x. Then I have my plus 1, and then all of this is over 2y plus x squared. I forgot to put my squared on the last step. It's the denominator squared for the last part of the quotient rule. Okay, so everything works out really nicely in this first term. See how we have some complex fractions? So we have a little more simplifying we need to do here. Okay, everything works out great in this first term. 2y plus x cancels with 2y plus x. Negative times a negative is a positive. All right, so second derivative is equal to, we have just a y from that whole first term. Things do not work out quite as nicely over here. So first thing I'm going to do is I'm going to distribute my y in here and over here like that. I'm also going to multiply the 2 on top. So this is going to be a minus, because I have that minus up there, 2y squared divided by 2y plus x. And then y times 1 is plus y. All right, I'm going to do a real quick little simplify. We have a y plus y, so I'm going to write that as 2y minus 2y squared over 2y plus x, all over 2y plus x squared. Still have a complex fraction, so I'm still doing a little bit more work here. No negative exponents, no complex fractions. So to get rid of my complex fraction, I need to multiply this numerator by 2y plus x. That's going to distribute to both terms. All right, second derivative is equal to 2y. All right, I'm doing like a lot of distributing here. So when I distribute my 2y plus x to this first term, I'm now going to distribute the 2y inside the 2y plus x. So 2y times 2y is 4y squared. And 2y times x is 2xy. Then I have my minus sign. And then when I distribute 2y plus x to this term, the 2y plus x's cancel. And I'm left with minus 2y squared all over, oh, I didn't write this. So when I multiply the top, I have to multiply the bottom by the same thing. So now I have 2y plus x cubed on the bottom. Multiply them together, add their exponents. All right, we are basically there now. We have a 4y squared minus a 2y squared, so that's 2y squared plus xy, all over 2y plus x cubed. Okay. 2xy. I keep making little errors, but I'm catching them before I stop the video, so that's good. 2xy. All right, and then if you did the calculator thing, so same way we did before, I'm sure they would factor out the 2 from the top like this. So y squared plus xy. And I believe this is the answer the calculator will give you, just like that. But there is actually a little more you could do. All right, this isn't a required step, but I think it's really cool, so I like to show it to you. So look at that, y squared plus xy. Might look familiar. Go back to the original problem. Y squared plus xy. We know y squared plus xy is equal to 25. So we can do a substitution there. 2 parentheses, plug in 25 for y squared plus xy. And then just multiply those together, and we get 50 over 2y plus x cubed. And that is such a clean answer. I love it. All right, that'll do it for our implicit day 1. So you got some homework down here. Hope you enjoyed the video, and I'll see you on the next one. Lights just turned out on me. Kind of crazy there.